Today we will learn how to assign a new material. Okay. So for that, first we need a pH curve for that material. So this is the pH curve for that material. We are taking it for 100 degrees Celsius. So just take some random values. You can take any number of values you want, but try to take like 10 or more values. Okay. So for example, I'm taking like -15. This is H and the corresponding B value. -15, then 0, 13, 25, 50, 75, this 75, 100, 125. I'm taking like random H values and corresponding to it, I'll find what is my B value from pH curve only. Okay. So example, this is my -15 value. So corresponding B value is 0, right? So here it is 0. Then second, I'll see for 0 value. Second, I have taken 0, right? So I'll see for 0 what is the corresponding B value, right? So this is 150. It will be around 125, right?
Yes.
So 125. So similarly, for other H value also, you can find the corresponding B value. You understood this part?
Yes.
Yeah. Now, yeah, like that in the previous class, you were getting confused on how to find alpha, beta, right? This part is clear, right? From BH curve, for like you can take multiple H values. I'm taking like 10 H values, and I'll just write the corresponding B values and will fill that in the table. So BH curve is done, right? Now, second thing is, because I want to calculate my core loss, so there is one equation for that we call it as Steinmetz equation. This again write it, okay? So there is an equation to calculate core loss that we call it as Steinmetz equation. So this is that equation. Okay, these constants. This is frequency and this is flux density. Okay, fine. So now how to calculate alpha and beta and k value, because these are constants, right? So first, for calculating alpha value, this is the formula, which is like log PV2 upon PV1 upon log F2 upon F1 when B is constant. But what I meant by this is, means how to calculate this is, we again have to go to our data sheet and see the P versus PV curve. Okay, flux density versus core loss uh, curve, right? So first, what we will do is, alpha is log PV2 upon PV1 log F2 upon F1 when B is constant. So first thing what we will do, because we have F2 and F1, we have this is for four frequencies, right? 200, 100, 50, 25. You can choose any two of them because we just want F2 and means just we just want two frequencies. So you can choose any two frequencies from this. Example, I'll choose 200 and 100 kilohertz. Okay, you can choose anything. It does not matter. Okay, then I'll see. But one thing is important that B should be constant for them. Like example, if I'm choosing 100 millitesla as B value, then you can see that for 100 Tesla, this and this I cannot choose, right? Because I don't have any, like this is not getting in, uh, it's not intersecting with this. Like, you are understanding what I'm trying to say? Because if you choose 100, then you cannot choose 50 and 25 because you can get for 25, like PV value you can get for 50, but you cannot get for 25 if you choose B as 100. So then if you are choosing 50 and 25, then you have to choose some other B like this. Okay. So first you have to see which B you want to choose and if you are getting the corresponding PV value through it, or if that graph is like if that graph is cutting that B value. You are understanding what I'm trying to say? Is it clear or like it's confusing? Okay, like I'll tell you by example. Suppose I choose 50 kilohertz and 25 kilohertz as my frequency, right? F2 and F1. And I choose my constant B to be 100. Okay. So if I choose 100, I can see that I can only get PV value for 50 kilohertz, right? This value, right? But I will not get that PV value for 25 kilohertz. That's why either I have to change my frequency or have to change my B value. Now you understood? Are you understanding this? Okay, fine. So we will, I told you that I'll choose like 200 and 100, 200 and 100, and I'll take my B value as 100. Okay. So I'll just draw one line from 100, uh, from B equals to 100. Then I'll see what is my corresponding P value. So it will be PV2, PV1, and F2 and F1 will be 200. F2 will be 200 kilohertz and F1 will be 100 kilohertz. So in this formula, you can put it and can calculate alpha. You understood this? How to calculate alpha now?
Yes,
Good. Similarly for beta, what is our formula for beta? It's log PV2 upon PV1 log B2 upon B1 at F constant. Now what we will do is we will keep our frequency constant. So any frequency you can choose. I am choosing example 100 kilohertz. So for two B values, example this 1000 and some value here, I'll write the corresponding PV1 and PV2 value. So now PV B2 will be this value, B1 will be 100 millitesla, and P2 PV2 will be this value and PV1 will be this value. Here I have chosen 100 kilohertz. You can choose any frequency. You can just put this value and you can calculate beta. You understood this?
As
First, yeah. So first we have kept B constant and here we will keep frequency constant. So now we got alpha and beta. This is logarithmic scale, so I'll not be able to find the correct values. You have to use some app or something to find the values. Like it's difficult, right? So you have to use some app or something to find the correct points and correct values. It will take some time, okay? Fine. That's why I'm not calculating it here. Fine. And then we have K. So now we know that PV is equals to K F alpha B beta. So now K will be just PV upon F alpha B beta. So you already know the value of alpha beta, you just calculated, right? Take some frequency, beta value and PV value. Example here, take 100 kilohertz as your frequency, 100 millitesla as your B value, and then just the corresponding PV as your PV value, and then you can find K. Understood? Understood this? Right. So this is how we have calculated alpha, beta, and K value, right? Now let's move on to our simulation. Now you understood, no?
yes,
I'll just stop sharing from this. Okay, so this was our geometry, right? Let's see how to assign it, assign the material. Just go to rectangle one. Let's rename it as 4. Okay. Then ferrite, edit, edit. In material, we have to edit, then add material here. change this to non-linear. Then BH curve, you have to go to BH curve. Actually, you can import, see, you can make one Excel file and import data set also. But what we will be doing is we will just add, means we will just add the values here only. Okay. So you understand this now, how we have we got these values that I am entering.
Ma'am, can you repeat once again?
For that, I again have to switch to my iPad actually. Okay, I'll just tell you. Fine. Okay. So the uh, BH table that you have just seen, that we got from here, right? This is H.
Ma'am, this fine, ma'am. Uh,
Then
n-
what you
uh,
want?
then material, assigning
Oh,
material.
okay, okay, okay. Okay, okay, fine. Okay, then I thought you did unless this. Okay, fine. Yes. Okay. You remember how we assign materials? What we do is
Yes,
we click on the geometry, then on material, right? And edit, right? And here we type our material, what we want. If it is present by default here, but this is not, we now we are not using the default present material, we are adding our own material. So what we will do is we will click on add material. Okay. Then this screen will appear. Okay. Then here you have to, in relative permeability, you have to select non-linear. Okay. Then here be it, in front of that you will see BH curve. Click on that BH curve. This uh, this will pop up. Okay, fine. And here
yes,
you have to enter your B and H value. Now you understood?
yes, ma'am.
Fine. Here we will enter our B and H values that we got from our BH curve. Okay. You can like you can put any number of values, and I'm just putting 10 values here. Then change this to millitesla because it was in millitesla. This was an ampere per meter only. Then click OK here. Fine. Now here in core loss model, you have to select power ferrite. Then This Cm is your K value, which we calculated as 12. Then X is your alpha value, which I got as 1.3. And beta is your Y value, which is 2.55. Okay, when you will calculate it, you will get some. See, it is on your assumption, right? So what frequency you assume, what B you assume, right? So it's not like you will get the same values, but you will get more or less near to this values only. Okay, so whatever you get, put here. Okay, it's not like everyone will get same value, because it is based on your assumptions, right? Just click OK. We will change the material name to 3C85. Okay. So now you understood how we have assigned add a new material here. Okay. Should we proceed? Okay. So now the next step is excitation. So the geometry we have drawn is inductor. So it has just two terminal, one positive terminal, one is negative terminal. I already told you how we assign a positive and negative. Okay, you remember, right?
Yes.
So it depends on how your current is flowing, whether it is flowing in positive y direction or negative y direction. Fine. So here I'll tell you one more like how to add uh, excitation in some other way also. So here we will select excitation, then add winding. Here we will select current only. Now I want AC current, right? Uh, we are doing transient analysis. So I want AC current, which is 10 sine omega t, right? So we will write here 10 into sine omega is 2 pi f. I'm assuming my frequency to be 10 kilohertz. Okay. So that is what I'm putting here into time. This is just t, omega t. Okay. 2 pi f t. Understood?
Yes.
Yeah. So in transformer, what we did, we have assigned excitation directly, plus 10, minus 10, like this, right? Like 10 and then negative and positive. Like this we did, right? We can do this here also, but this is like the easy way. Okay. And in transformer also, we can assign winding and just give one value to here and assign the coil terminals there. So both can be done. It's not like this is done for inductor, or this is just this is done for transformer. It's not like this. This is just another way to assign excitation. Understood? Then we will click OK. So this is for my positive winding. Positive. Then we will again add one winding, which will be for my negative current. 10 sine 2 pi f into time, right? Then, okay. Now what we have to do is, we have winding. Now we have to assign coil here. So what we will do, we will first click on the first conductor, right click, assign excitation, and here coil. Okay. Conductor 1 positive. This direction, I told you, it's depending how your current is flowing. Okay. Then second, and see, I'll just give you an example. If you have assigned a current excitation, like we did in our previous, like in transformer, here also we can do that, right? But this is like just one of the way to do this. Okay. Here it's negative, right? This side, this one is positive, this is negative. Don't think of it as transformer, okay? There we were having four terminals, like two for primary, two for secondary, right? We were having primary and secondary. Here we just have one winding, okay? Only two terminals. That's why don't think like, ma'am, there we have taken like primary, secondary, and here why we are doing all positive and all negative thing. Just think that a transformer has four terminals and inductor just has two terminals. Okay. Then click on winding, add coils. Which are negative coils? This. Right. You can rename it for the ease of understanding, okay, I have not renamed it, but you guys please rename it. Okay. Then in P, add coils. The remaining coils we will add them. Okay. So now our excitation is done. Our material is done. Now in excitation, if you want to calculate your core loss, go first go to excitation, right click it, set core loss and select core, which was your which was your core? It's a rectangle one, right? If we rename it, it will be easy for us. See, renaming things will help you to understand, right? You don't have to look again which rectangle is which. Okay. That's why let's keep this practice to rename the things. Like if you are uh, drawing one winding, so just write winding there. Like don't keep it as rectangle 5. Winding 1, winding 2, positive, negative. Just like rename the things. Okay. So to calculate core loss, go to excitation, set core loss, and select this. Okay. Then click on OK. Fine. So now boundary is done, excitation is done. You don't have to do anything in parameters. Then mesh operation. Mesh operation is just like transform. Assign mesh operation inside selection, length base. This you remember, right? Mesh operation. Then in analysis, add solution setup. Here you will get stop time and time step. So our frequency is 10 kilohertz, right? So this stop time will depend on how much cycles you want. Like when you will plot your graph, how much cycles you want here. Like till how much cycle you want to analyze this. Okay. Example, if I want like 3 cycles, so it will be around 300 microseconds, right? And this is the time step. Like time step is like after it will plot time wise, right? So after 300 to 2 microsecond, it will give another. So like that, continuity. Then safe field. See, a safe field is important because when you want to plot your field overlay, when you want to see your flux density plot, you have to means it should save the field at every movement, right? That's why you have to save your field so that it will be able to show you your flux density plot at every seconds or every timestamp. Okay. So I'll just start from 0, then I'll end at 300 microseconds. Step size, so on this distance, you will get your field plots. Okay. Why it is important, I will just tell you. Fine. Then click on OK. Optimetrics, you don't need. Then see, validate your model. Now we will just run it. It's taking some time to do. Till that time, does anyone has any doubt? You can ask now because it is taking some time to run anyways. You guys have any doubt?
Ma'am, in excitation, how like a sine term of current? Can you explain once, ma'am?
What? Please repeat your question.
Excitation, current excitation,
So you
assigning
want to
current in sinusoidal form.
just write there 10 sine omega t, right? So you have to replace your omega by 2 pi f. Okay, I'll just tell you after this. It's like you have to write that 10 sine sin sine means 10 into sine, then in bracket 2 into pi. You can either write pi or you can write 3.14 into f. What is the value of f for us? It's 10 kilohertz, right? So we will write
Yes, ma'am.
10 000, like in SI unit you have to write now. That's why I'll write 10 kilohertz and then into time. So I have to write time time. So this thing, whole thing I have to write like in words. So it will give you that sinusoidal excitation. 10 sine omega t. So whatever your current is, you have to write it in this way. So magnitude and then whatever frequency and all, you have to write it in this way. You understood it or like after this I'll just I think it should this you are asking now, right? Hello?
Yes,
Yeah, so you have to write it in this form. This is 10 sine omega t and my frequency was 10 kilohertz. That's why I've written it as 10 sine omega is 2 pi f. 2 into pi into your frequency.
ma'am, that's okay, ma'am.
Yeah. Then what is your
Uh,
doubt?
that applying on winding current, ma'am. How it is applying?
In the same way, Like how it is applied.
There is a
See, I have given this as coil terminal, right? So all this coil will carry the same current as this winding. So I don't have to assign it individually to all. Understood? Understood why I'm using winding here? One thing is you can assign individually. The second thing is you can make one winding and put the coil terminals in it so that all will carry the same current. So this is just the other way to do that. Am I understanding your doubt correctly? I'm still not sure actually.
okay, ma'am.
No,
Understood.
like uh, you like you can ask. I'm not sure whether I've understood your doubt or not. So you can repeat it or you can just explain in brief. I'm not sure.
Ma'am, by
Understood,
selecting
right?
the windings,
Mm-hmm.
hello, ma'am.
Yeah, yeah, yeah.
By selecting the one side of the windings, half side of the transformer, uh, by right clicking assigning excitation, there is only few options are in front of us, ma'am. Like current density, permanent magnet field, set magnetization computation.
This now. So I've
Ma'am,
choose
these
coil
all
here.
options not came, ma'am.
It's
Current
not
density
there.
coil. No, ma'am.
Uh, Change your setup first. Solution setup. You will not get most of the option if your solution setup is not correct. Okay.
Okay,
Now you will get. So most of the options you will not get if your solution setup is not correct because magnetostatic deals with DC current, right? So here what will happen is if even while assigning the new material and just even these options will not come if your solution setup is not set to eddy current or transient, right? So it
yes,
is important that your solution setup should be correct. Okay. Now you're getting that option.
yes,
Yeah, you know how to change this solution setup, right? Right click on this solution type and then select transient. I told you this, right?
yes,
It's taking a lot of time for us. Okay, 5 minutes. Mm, it's clear now?
yes,
Yeah, fine. Actually, I think we can see it like this. Yeah. So actually, this is the same geometry. Um, I've already run this. So should we analyze this then? Because this is taking a lot of time to run. I think it's done. Yeah, it's done. Okay, fine, it's done. We can analyze our geometry. Hmm. So then we will go to results, transient report, rectangular plot, time, loss, and core loss. So this is your core loss. So here you can even So the average of this will be your core loss. But you can see that till around 50 microsecond, you are getting some random value, right? After that only, you are getting the expected curve. So what you can do is extract this. So extract the values from this, plot it in different app, and then like MATLAB, you know how to like find average value in MATLAB of a curve? You guys know
How
how to use MATLAB?
we are still in E3 sem 1, ma'am. Not yet completed that subject MATLAB. In next
Uh,
semester, I think, ma'am.
okay, okay. Next semester. Okay, define. Okay, then okay. For now, I'll just tell you. So this is the random value. Okay. Uh, but the average is we want is after this point. After this point, I want the average to find my core loss. Okay. So I don't give any any random value as my core loss. I want if I want like uh some perfect value, I can say. So what I'll do is I'll just see you have two options. Either you can just export from here also as a CSV file. Okay. You can save it anywhere. Okay. And then just don't use this values till this point and plot it from here and find the average. How to do that? I'll tell you tomorrow in like first 5 minutes. Okay. Fine. Through MATLAB only I'll tell. Fine. I thought you guys already know this. So that's why I've not prepared that thing. So it's fine. In like the first 5 minutes, I'll tell you how to find that. Okay. This is your core loss. Also, you can see one thing, like one mistake that I also did when I plotted this first time is in excitation, I forgot to set core loss. Okay, so don't forget it ever. Please do this. Okay, please select it. Okay, and then uh, results you can also see your current finding current. See, this is what we gave, right? 10 sine omega t. Well, now let's talk about field. So now core loss you understood how to get in the next class. In the first 5 minutes, I'll tell you how to find its average by just like eliminating the before values, right? So don't worry about that for now. But through Ansys you understood, right? Okay. Should we proceed with our field flux density? Select the geometry, then field B. You're, can you see you are like getting nothing here? This is because you have to set some time here. Okay. So let's set it to 124 microseconds. And set it to any value. I'm setting it to 124 because that is the peak of our current. Okay. Just wait a minute. My laptop is not functioning. Wait a minute. Can you see? You have to set it to some value. It's 120 microsecond for now. To see the field. So it will give you field as per your like your current is varying sinusoidally, right? So your field will also get vary with respect to that. So now you want to see how your field is varying. So one thing you can do is you can animate it. So this were the timings that we selected in analysis, right? So on this timings, we can see how our field is varying in form of animation. So it's running. Just wait a minute. Can you see? With respect to time, you can see how your field is varying. You can even change the speed and all. From here, you can even export this file. Okay, understood? So, you guys have any doubt till now? Any questions? Any doubts? Mhm. So, one Actually, there are some advanced things I wanted you to know, but I think it will be like too much for you guys because you will not use it now, right? So first thing is, I'll just tell you if you like. It's not related to simulation things, but it is more like a core loss thing. So I'll just tell you a few things about core loss. Fine. So first is Steinmetz equation, right? The equation that we have seen, mm, that we use to calculate alpha beta values, right? So when you will calculate your core loss from that, and when you will calculate from this, like when you will see from this, you will might find some like deviation, right? This is because your core loss, your Steinmetz equation works for like uniform flux density, right? And here you have seen, and here you have seen already, right? Your I'll just show you. Okay? So just wait a minute, it's running. So this is like one like this. So, but here you can see that your flux density is not uniform, right? It's not uniform, right? Even at one fixed timing, it's not uniform. That's why you will see some deviation when you calculate your PV from Ansys and from Steinmetz equation. So how to get like a perfect like a, what you say uh like minimum deviation, there is a way, but I don't think like it's that important for you guys now. So maybe I'll skip that part if it is fine. Okay, fine. Because this is already too much for you to understand. And even if you understand how to plot the flux density, how to get core loss, and how to like get winding loss and all, it's more than enough for you guys at this stage. And later when you will explore ANSYS, that time you will learn by yourself also. Okay, fine. So do you guys have any doubts? So we are complete with we are done with our 2D geometry. So till till now we have covered transformers. Then we have seen all this like how to draw transformer geometry, how to draw inductor geometry, then how to assign excitations, how to do solution setup in eddy current, and how to do it in transient, right? Then what we completed, mesh operation, boundaries, and all. Now you understood how to set up analysis for eddy current as well as for transient. Now you guys know already. So I think we are done with our 2D structures. From tomorrow, we will start with 3D transformers. So there, uh, we will not go in that much deep. We will just see how to draw the 3D transformer geometry, and then we will just do the AC analysis, like transient analysis of it. I think it's more than enough for 3D geometry because you have already done so much in 2D geometry, so you will not find it that much difficult. Right? So if you guys have any doubt, please ask me, uh, or else we're done for today. You guys have any doubt? You want to ask anything? You want me to repeat anything?